So, hello everyone. Thank you everyone for coming. Thank you everyone who joined online to the next edition of Mython AI Times. A little bit of organization. Feel free to grab any drinks or food you see. Also, after the talk, there will be more refreshments coming, so feel free to stick around and talk, right? But I believe that, we are all here today to hear Dr. Markus Lnage, who came from DLR from Germany, which is German Aerospace Institute, I believe. Sorry, I think
It's fine.
sorry about that. German Aerospace Center, right, is the correct translation. Thanks. Which is, I believe, the largest part of European Space Agency as well, on top of being a very good and well-known research institute. Markus, I believe, traditionally is or comes from a field that I would call mathematical physics, right? He's a mathematician. He got his PhD in mathematics at Friedrich Schiller University in Jena, and I have known him to work on problems in functional analysis, I would say. But nowadays, he has been spending time at DLR, as I mentioned, and he's working on problems that are related to trusting the machine learning models. And that I believe to be the topic of today's talk. So yeah, the floor is yours, Markus.
Yeah, thank you very much. Okay. I hope I'm hearable. Yeah, I hear myself. That's good. Yeah. So thank you for the invitation. Thank you for giving me the chance to speak here. And let's see if this works. Yes. Okay, so I probably don't have to tell you that AI is everywhere, and that somehow the domains and applications are growing for these kind of systems. And especially also in the German Aerospace Center, we have a lot of different institutes working on topics related to AI. Probably not finance, but we also have huge many institutes to work on energy, on health related stuff. Security and defense is there, and also the big spot of the aeronautics and aerospace. And in particular, I'm not okay. Oh, okay. Then let's have the online audience also see what I'm mentioning. Okay. So yeah, great. Okay, so at the German Aerospace Center, we have, for example, institutes work with AI on Earth observation, on predicting maintenance, a huge group where actually also our institutes belongs to on autonomous driving vehicles and robots. And actually the DLR invested also a lot of money to put this nice flying cube there in space with an astronaut to see how these personal assistants could work. And so you see, we have a lot of applications and a lot of different use cases where we are interested in understanding AI. And many of these institutes are working with AI. And our institute, which is the Institute on AI Safety and Security, actually has as the main mission to somehow make AI also available in safety critical applications. So, for example, if you think about autonomous driving vehicles, you want to be sure that the AI always knows what it's doing, or at least lets you know if it doesn't know what it's doing, so that you as the maybe still driver in the seat can then decide to take over. The same with if you use AI in some rockets to do the right mixing of the propellant and stuff like that, and the right trajectory, you actually want to know that the AI system always is at least within some safety constraints of what it should be doing. And this is where our institute is mainly working on. So I will do some advertisement of the institute and then come to some use cases, but bear with me. So the institute itself is mostly concentrated on these 3 points here. So we want to have a safe and standard compliant AI system, not only at its introduction, but actually over the whole life cycle of the system. where especially the AI Engineering Institute department is mainly working on to actually integrate this into the whole life cycle of the system. And to continuous updates, together with the Algorithms and Hybrid Solutions department, where we somehow investigate and do research on how to do actually this uncertainty estimation, how we can actually certify certain aspects of the AI and guarantee safety there. Then we have the Safety Critical Data Infrastructure department working mostly on cybersecurity and resilience. So that's the data part. It's not only the algorithm that needs to be safe, but actually also the data should have some quality. You need to be able to actually say in advance that certain data may not be useful because it's not clean enough, or there are some other problems with the data, so you need to do some more pre-processing. And all these systems are somehow investigated by this department. And overall, they want to somehow integrate this into a bigger data space system where you can then somehow be sure that even if you have data from a different company, which might share only certain parts of the data, you can still trust the data you get and work with it up to some specific level, right? You might not know everything, but you can at least be sure I can use this for certain cases. And also they are working, have a huge part working on federated learning approaches, where then actually different companies can share their data without giving the data away to other competitors, and still can use the overall machine learning model that comes out of this data. And the main use case for us is this autonomous mobility and logistics facilitation, which is a fancy word, but in the end, it's somehow robotic systems. I will have some examples later. And there, especially, we need this last department there, which is the executive environments and innovative computing methods, where they actually see how you can actually use AI system on some edge devices, on some FPGAs, for example, or also shoot them into space and put them onto some satellites where you have some resource constraints you have to think about before actually deploying the AI. And we also have a group working on quantum computing there, and somehow combining machine learning with quantum computing and doing quantum machine learning. Overall, the Institute also has some departments working on the transfer, so getting our research out into the open world, and a group working on business development, as well as this ELSA team, which stands for Ethical, Legal, and Social Aspects of AI. So we want to think about also the aspects of the ethics and the social aspects of AI to actually combine everything and get to know how our AI systems can be perceived by the general public and how we can make them use them in a good way. Let's call it like that. Okay, let me continue on. Before I come to some more use cases that we specifically work on, let me give you a short aspect of examples where you might think that safety-related aspects might be useful in the AI. The first example is this. So imagine some 10, 15 years from now, you have some robots actually performing some surgery on yourself, and then you probably want to be sure that it does not somehow mistake your liver for some cancer. So these kind of robots are already in use. They are not used by AI, they are used by the surgeon. So the surgeon actually, a human tells the robot or uses these robots to do minimally invasive surgery. But you can imagine it's not far from there to actually use then AI to do all these things, at least helping the surgeon in doing stuff. And then you want to be sure that actually the AI system at least tells you when it doesn't know what to do next. Another example would be this fellow here, which is somehow a handyman robot, one could say, which actually is able to do some basic tasks with these kind of machines. Currently, everything is controlled somehow by some pre-programmed symbolic AI systems, but you could also throw some sub-symbolic AI systems on this and somehow train it on a big bunch of data, maybe in some human feedback loop where it somehow watches videos of some handyman drilling some holes into a wall, and then should try to do it itself. And then in the end, you actually want to evaluate, has this learned to drill holes into a specific part of the wall, or is it just someone screwing around and doing whatever. Probably you will see it, but if you really want to have them in your home to work with, then you should be sure that. Another thing would be this kind of use case here, where you have a huge robotic machine working and you have some human. Okay, in this case, he's actually controlling the arm, but you could imagine he's just doing something else down there. And then you definitely want to be sure that this robot arm always knows where this human is and does not do some movements and kills the human in the way or injures him. And there also, it's very important to understand how sure can we be that the somehow environmental perception of the AI system is good enough to guarantee safety, in this case, between the robot and the human interaction. Okay, so I hope this gave some idea why it is important to think about safety. And one way to think about safety is to understand the robustness of our AI system. So robustness in the end means that if I have small perturbations in my data, I'm sure that I'm not somehow certainly having a completely different outcome of my AI system. If you now think about classification, for example, if it sees different pictures of a cat, then small changes in the pixels, which we might not see even as a human, should not probably change the classification to a dog, if it's a picture of a cat. And there are different ways to somehow understand this. And one way is we can understand the uncertainty quantification. So we can understand how much is the errors in the system related to not having enough data. So can we increase the reliability of the AI system by just giving it more data? And what are actually some inherent problems of the system due to, for example, data noise, sensor noise, and other stochastic events that are just there in the data that we will never get rid of. But at least if we can quantify this, then we know where we can improve our system and where we have no chance and have to have some other way to guarantee safety there. Okay, as an example here, some data. In a perfect world, we would have perfect data. So you can imagine you have some sensor, or actually we have some sensors via some company in the German railway system. And you can imagine, okay, if there's a freight train going over the sensor, I have this signal. If it's a regional train, I have this signal. And if it's a long distance train, I have this signal. I imagine that also you as humans can now actually distinguish these two signals, these three signals. The problem is the data is not that nice if you have it in real world. And you see there's a lot of different things happening there. And so obviously you can do some pre-processing, you can get rid of some outliers, then it's much nicer. But even though all of these signals still seem to be nice, right? This could be a freight train, that's maybe a regional train, but you're never quite sure. So to train an AI system on this is quite hard. We did some work there, we got rid of the anomalies, and our system is somewhat okay-ish doing this. It's not perfect, but it's also not a big data sample there because I had to rerun it on Monday to get some new data there because we changed a bit of the algorithm. So the bigger system is still running, unfortunately. But you see, we have some confidence of the system here. That's bad. Okay, I'm not doing that. We have some confidence that most of the signals are actually classified right. And if you look down there, you actually see that some of the true labels are in rows and the predicted labels are in column. That in most cases it actually got it right. But at some cases it actually didn't get it right. And as you can see here, it also is not so confident. So actually in the cargo train, Güter, sorry, I didn't translate. Sorry, it has some. It's not so confident with some of the samples, but it actually got them right. So that's fine. And there's some work to do, some more working there. But again, it's somehow a quite easy task in a way because you have this one-dimensional time series data which you can go through. There's not much that can happen, and in the end, you just have to classify it in our case now in 3 different samples. Okay, you could go on and say, okay, which kind of cargo train is it? Was it an ICE3 or an ICE2 and so on? But that will not be able, that we will definitely not be able to do with a simple system. Then you have to do some Excel counting things to distinguish between the trains, how long they are and so on. So there is some work to do, but this basic system somehow seems to be at least able to classify most of the trains. But you can imagine you go into a system where you actually are not in a simple system with one sensor taking some measurements, but actually you now have some segmentation problem, right? You have some data, for example, from some autonomous car, in this case from a camera or from some LiDAR sensor or some other sensors, and you might have multiple sensors there, want to combine them, and then you actually need to understand, okay, how can I distinguish what is the uncertainty there that I can get rid of with more data, and what is the uncertainty I cannot get rid of whatever I do. And with this, this brings us to this aleatoric and epistemic uncertainty, where you see here the ground truth, so the segmentation somehow in the third part of the camera, of the AI system, and you see, for example, down here that it didn't see this traffic light pole completely, and also the walking pathway here, it has some problems. And you see there that at least the walking pathway, most of the stuff you could actually solve by giving the AI system more data, because it's epistemic uncertainty. So data related, if you just train it a bit more on what actually a pathway is or how these pictures look like, then you might actually get rid of this quite easily. On the other hand, if you look at the upper row here, you see that all the pixels behind this car, they are mostly in the aleatoric uncertainty area, because the sensor is just not good enough to actually distinguish what's happening there. The sensor will not be able there. But you could now somehow combine it with additional sensors to actually also get this information out. And then you, in a way, can change aleatoric uncertainty into epistemic uncertainty by somehow combining it differently. And also the other way around, if you have a crappy sensor, you will probably have a lot of aleatoric uncertainty, because you cannot get rid of this by giving it just more data. But this, in a way, gives us a possibility to actually understand what the system can better know with more data, and what we will never know and can never get rid of in the end. And somehow where the system should definitely say, hey, I cannot distinguish what's back there. The question is, does it need to distinguish it right now, right? It could say, somehow in 3 minutes when I'm there, then I can distinguish what it is. But anyhow, somehow this kind of things then say us, okay, if we want to know what's in this pixel, we will not see it. We will not get it out of the system, whatever we do at this point in time. And this somehow gives us a way to say, I don't know what I'm doing, at least in this part of aleatoric uncertainty, where I cannot distinguish this. Where we used this kind of segmentation in a project we had was with some, okay, maybe I can go on. Does it then start? So we have this, okay, at least we see it here. We have these walking tablets here, which have a different set of sensors. They have the camera, they have a LiDAR sensor, they have some other sensors. And we can use this data to also do some segmentation and actually understand the aleatoric and in retrospect, the epistemic uncertainty we have in the system. And it is trained on somehow not, in a way, not harming humans, but somehow always seeing where the human is, and then somehow respecting the human and not somehow bumping into it. But still, it needs to keep balance on what it's doing. Okay, it's not playing. Can I play it here? It's not so important, but okay, it doesn't play. Whatever. No, it's not. Maybe here. Oh, okay. Whatever. What you would see is this woman here runs around on these points and doing strange movements, and the robot is going around and still somehow keeps balance and can go around, and sometimes has to stop. It's also only a small sequence. It's not so important. But the important thing is we can somehow say, with these kind of uncertainty estimation, does the robot system still, in a way, see the human? Does it know what to do to not bump into the human or not? And that you really see here in this kind of graph, which is somehow taking an average of the uncertainty of the system over time. And you see here there's the still image. So the still image is taken at the end where the last point is, more or less. And you see it sees the human. The human does whatever he or she is doing there. But the system is quite certain that somehow it knows where the human is, which is good, right? He's directly in front of the camera in this case. And in the next picture, you can probably guess that the human here is hiding at this point here behind this machine that is there. And the system actually doesn't know where the human anymore is, right? Before we were somehow here at this point, it was clear, then the human moved away, so it had some uncertainty. Then it saw it again, and then somehow the human was not distinguishable anymore from this machine that is standing there. And the system the uncertainty goes up above this threshold, and the system can now say, hey, I don't know where the human is, either call for help or use some other sensors or whatever. And we can somehow always say, okay, it's probably not safe to move around now. Even, okay, for this running tablet, probably it's not bad, but if you would now think about this huge robot arm I had in this picture, the robot arm should probably not do any big movements anymore, but first of all, try to get to know where the human is again, to not harm the person or destroy another robot or whatever, right? So these kind of uncertainty estimation is quite helpful for us to guarantee some safety, that at least at the point where we are not sure where, in this case, the human or whatever else is, and the system cannot distinguish this, we say, okay, stop, call for help, do whatever, but don't do your programming on as you would usually do. And in this way, we can somehow give some at least basic safety guarantees there. Okay, where we want to use this in the end is a bigger project we are just currently setting up, where you can imagine a big workshop where, for example, a robot arm and some autonomous vehicles work together, and you also have some humans there, here depicted with some VR goggles, because that's also should be all set up into a digital twin in the end. But you can really imagine, okay, you have some system where you have some loading, unloading of boxes, whatever, right? The use case is not so important, but you have some interaction between different robotic systems and humans, which are in the loop. And you really want to give guarantees that nothing goes wrong. And most importantly, you don't have to cage everything where a robot is working like we have to currently do, because in a way we can guarantee some safety aspects there. What's important there is this kind of verification, where we'll come to in the second part. Oh shit, okay, we go on here, where you either can give maybe deterministic guarantees, so you can really somehow write down what the system is doing, for example, in some symbolic code with some logic, and you can really say, if this happens, then this happens, then this happens, and with this way you can then guarantee there is no unsafe state that you will enter into, which is again somehow an ideal world, which you will maybe be able to do with just one robot. But if you have a human in there, then giving deterministic guarantees what this human will do while the robot is working, no chance in a way, right? But then you can at least give maybe some statistical guarantees, where you can somehow at least guarantee statistically when something happens that you are not prepared the robot for, then the robot will, for example, stop or something, right? You have some bounds there that if bad things happen, you can at least guarantee it will stop and nothing bad will happen. Or you can do this look before you leap refinements, where you somehow let the system always simulate up a few steps in the future. If I do this action, what will happen? And in this way, you can then again, if you would enter an unsafe state, whatever this is, depends on the use case, it will stop there. More on that later. And some approximate guarantees. And in this way, we will get, due to this verification, we can guarantee some safety, and we can also get some interpretability of our system, which is somehow the second part. It's good if you can give some safety, guarantees, but you also want to understand what's happening in the system and how can I maybe actually even more enhance my safety, or why does this somehow critical states happen, which you can do with some post hoc and ad hoc explanations, or somehow deciding between the instant and the model, what's the difference, so that we actually, in the end, if we are in a human in the loop situation, can actually give some. Okay, sorry for that. This I wanted to have. So we can actually do not end up in this situation where the AI system does something and the humans actually don't know why this is happening, which is definitely not what we want. Everything might be secure and safe, but we still want to understand what is happening there and have the control over everything, especially if we have these scenarios with a human in the loop. So imagine, as I said, also a human or more humans working in there. You still want to guarantee that the process is safe, even if the human does some stupid stuff. And let's be honest, humans do stupid stuff. And ways you can do this are, for example, these inverse reinforcement learning approaches, where somehow you have a human doing these tasks and the robot learning this, but not the way that the robot actually learns a policy by observing the rewards it gets, but actually by observing what rewards, that it learns the rewards by observing the policy of the human. And I will come on that to that in the second part now, where I will go into more details on how to verificate and validate an AI system on the basis of a certain project we have. And the project we have there is the following. And let me quickly grab something to drink. So the project we have there is called Safer Squared. It's a bigger project with a lot of institutes of the DLR involved. And we are there in a sub project where we actually work with this with a certain wing concept called Olaf, or on the basis of it, which we want to understand how we can use AI to actually make the wing fluttering of airplanes go away in a way. So currently, airplanes fly that slow that this wing flutter does not appear, because it would be bad if it can start to somehow accumulate and then at some point the wing will break. And currently there's no chance or there's no system to actually reduce this. So you have some safety margins and you just don't fly fast enough. But if you think about that, you want to make airplanes more efficient, you want to make them lighter, so the wings will get lighter, and you also want to fly faster. And in this way, you then enter the somehow boundary region where these kind of things might happen at some point. And for that, you then need a system that actually can control this. There are classical ways or classical controllers which are worked on to do this, which somehow work. I have an example later. They are based mostly on these H-infinity controllers, but the idea is to actually use an AI system to not only work while somehow you have always situations which you can program in. With these, you can use a classical controller because you somehow always know what happens. But if you're on an airplane, there will definitely be situations that your controller has not seen before. And then having an AI system doing this and being able somehow to generalize to the overall possibilities that might happen during the flight is actually the goal of this project. We are not there yet, just to tell you. So as I said, we want to show advantages of reinforcement learning over the traditional H-infinity controllers. And in the end, we actually want to understand what is actually needed to get these reinforcement learning based agents through a certification process. Because if you want to introduce them into some airplane, you have to go through the whole certification process of all these things that will be put in place for an airplane. And for that, we definitely need to give some safety guarantees that we are sure, even if the system completely loses control, we can somehow guarantee safety, at least on the basis of this H-infinity controller, which they also want to go get through the certification process. Okay, so how does this look like? We have this nice airplane and we have some wing flutter there. And this classical controller where our friends from the Institute AI, also Aeroelastics, are working on, has just controlled somehow the aileron of the wing to actually counteract this wing flutter and getting the system under control again. So you see that here, the red line is the closed loop, so where the controller is on, and you see there's no, you don't see anything, but if you would zoom in, you would see it starts to oscillate and then it gets caught in again. And you see the action of the controller here, so it really counteracts this fluttering and can control the system. In the open loop, where you don't have the controller on, you see it spirals out of control and you lose control very fast. And our reinforcement learning system should somehow learn to do this based on this data by exploring some of the data space there. Just as a quick introduction to reinforcement learning, in reinforcement learning, you have an agent, your AI system, which can interact with the environment and then observe what its action has done to the environment, and in the end project forward what the overall reward would be in the end if it would continue with its actions, and learn by this an optimal strategy to satisfy its task at hand, where the task is somehow encoded into this reward function you have there. Different kind of actions might get you to the same goal, but you might get less reward for certain somehow combinations of actions. And in this way, the agent can explore its environment. Now you have this problem of, do you want the agent to explore everything and getting to know the whole environment and what actions it can do and what it might have as a reaction onto the environment? Or do you want it to actually just find the fastest solution because you don't have enough time to train it everywhere, or you don't want to get it lost somewhere? And this this is some problem there where you have to see if you want to have it explore more or exploit what it has already learned. And that is some more intricate delicacy in this reward function to find the right way to do this. Okay, but in the end, we actually not want a simple reinforcement learning system to do this, but we want actually a safe reinforcement learning system because we need to give some safety guarantees. And there are different ways to do this. Many of them are based on some formal verification things or on some constrained Markov processes. And an extreme example that you definitely don't want to, that, for example, the agent decides to just crash the plane because that's the fastest way out of the fluttering of the wings, which might not be the best solution. So that's definitely something we should declare as an unsafe state and not have it do that. But it's then hard to decide what is unsafe now. So a bit of fluttering might be there and it might not be bad. So you might not want to restrict it to completely get rid of all the fluttering, but you definitely want it to restrict the fluttering if it gets too high. But if it is activated too late, it might not be able to somehow get the fluttering under control and things like that. And these kind of things we need to somehow encode into our AI system. And there are different ways to do this. First of all, we can use some constraints, right? We can really constrain it not to do certain things that you can do with this kind of reinforcement learning network here, where you not just have an actor and a critic, but you also have a risk network. And this risk network then decides if a certain action is too risky to take or not, or should not be taken in this situation where you currently are, because it might lead to some risky stuff later on. Obviously, to, in a way, do this, you need to have some knowledge of what are unsafe states. For example, crashing a plane is not a good way to do it. And this is somehow then depends a bit on your use case you are in and how you want to define this. But this is actually a way how you can do it quite easily, because sometimes you have just a risk network that is based on a neural network, which is not so easy to use. But sometimes you can actually symbolically define what is an unsafe state. And that's then a great thing, because that would give you some control and some safety about that this would never happen. And this brings us to the second case, where you have some formal verification methods. So in a way, you shield your system from the outside, you could say, where you always let your system explore your environment, but in the end, the actual action that is taken is always projected back onto some manifold of safe actions. So you're always sure that your system takes a safe action, but you might in the beginning not be sure, or obviously you're not sure, what the best combination of action is to actually keep the system safe. But by having this, the neural network explore the whole range of possible action it could take and always project back, it might find an optimal or even the best way to keep the system safe. And you as the user are always sure, I will only do actions that are actually pronounced safe in the current situation. There are setups for this, which somehow do this. And this kind of shielding process is also something we are really looking into to generalize to the system to really get some constraints that we can then also certify the system. Because the certification agency will definitely say, hey, can you guarantee in every situation that the system will be safe and will we keep the airplane under control? And with this kind of ansatz, if we make it work properly, then we can guarantee this because we always project back onto some action that is taken that is actually safe in the current situation the system is in. The idea there, is definitely that if you have some kind of H-infinity controller that you are sure can control your system, then you could use that as a shield, at least in the situations where you know it can control this. And then it's again the uncertainty that you have to investigate how many situations or when do I actually come into a situation where my H-infinity controller is not working properly anymore, and can my AI system still handle this, even though it only might project down onto certain actions that the H-infinity controller might be doing, but it might find a better way to actually use these actions than the H-infinity controller is doing, because that is a pre-programmed set of actions that is taken. Okay, and the last thing, okay, maybe, let's see if this video works. Hope. But maybe no. Why does it not work? Okay. Okay. Whatever. Let me just tell you what it would do. So this is a basic implementation of this shielding process we did. It would have been nice to show it to you. So this is the safety gym environment. Maybe some people of you know it. And this red dot here, in a way, moves around there. You can also have it as a racing car or whatever. It is not supposed to go into the violet things, but it is to go into the green thing. And then the green thing moves around and it has to find it again and so on. This box, it just can crash into it, doesn't die then, but it somehow it doesn't see what's in front of it if it crashes into this. And if you now could see this video, you would see that at this point, it would somehow, it's heading towards here and it wants to go there, but it has to stop first and then somehow turn a bit to go there. And it should not go in there. And then you would see that somehow some shielding activates because the AI agent wants to do certain moves, which would have brought it into this round violet thing here. But the shield kicks in and says, hey, this action is not what you're supposed to do because you would enter this unsafe region. And then it actually stops there. It wiggles a bit because somehow the AI agent fights against the shield. And at some point they decide, okay, we turn a bit more and then we can actually hit the green thing. And then the video goes on. The green thing will appear here. And the thing again starts, but it's programmed to go to the green thing as fast as possible. The problem is there's physics in there, right? So if you go very fast, you cannot turn a corner quite easy, right? So it will actually crash into this box here because it couldn't take the turn, and then couldn't see anything anymore. And then it will crash into, I think, this violet thing because the sensor which we used is just looking this part ahead and couldn't see it to the side. And then it actually tries still to get to the green thing, which moved there. and will crush in here because it didn't see it because of the sensor. So you see, you definitely shielding works, but you also need to give the system enough information to actually use the shielding in all situations. If you have certain blind spots, it will not work, which is somehow quite obvious. And I'm sorry that the video didn't work. Okay, but there you see shielding can work if you have enough information for the system. And then you can give some safety guarantees, because as long as somehow the shield is able to perceive its environment, it will hinder the AI agent to do some unsafe actions and enter these unsafe states. As the last approach to safe reinforcement learning, and it's the current approach we actually use for the system I talked about, is actually this human demonstration and pre-training in a way that we use this H-infinity controller, which is able to actually solve these environments, is used as the training objective. I have some slides later where I go there. But the idea is that you somehow have your AI agent learn the safe behavior that some human or some working system in a way does. And in the end, it might then actually learn some additional ways to actually solve this environment that maybe the human didn't see, but at least it will be constrained by what the human already knows, what is a good policy and what is a bad policy. Okay, and in this way, we, in a way, then have to combine it probably with this formal verification to have some really safe guarantees, because you might not see directly that the policy that the system has learned is safe, but at least you can somehow get the feeling that if it uses the human experience as a first training steps, it already knows what it might need to do and what might be a bad idea to do. Okay. So here's the current setup. How am I out of time? I should finish probably at some. Okay. So it's not many slides. So here's the current setup. We have this environment here, which somehow enters the system into our experience buffer. And then we have imitation loss, which is somehow this H-infinity controller, which somehow tells the agent what would be a good action. And we also have the proposed action of our soft actor critic loss, which somehow trains the agent. As we will see later in the current setup, we mostly use the imitation loss to actually get the system running. We started first without the imitation loss, and the system actually didn't learn anything. It was just a too complicated environment, because actually the environment to have this wing flutter control, like they use it for the H-infinity controller, it has 10,000 steps per second. And long reinforcement learning usually uses 10,000 steps over the whole episode. But to have it stable for 5 seconds, you actually need 50,000 steps. So it's a huge amount of time that it has to somehow control this. And this is a very complicated thing, which makes this a very complicated environment to solve. But anyhow, the idea is that the agent should somehow imitate what the H-infinity controller is doing, learning what are safe actions in certain situations, and then perform this somehow later on without the H-infinity controller. As you can see here in this preliminary result, in the beginning, the first 400 episodes, we had this H-infinity controller on as a guidance, and then reduced slightly over the 400 episodes how much influence it has on the perceived action that is taken. And then you see it drops, right? It seems like it has learned nothing, but then it somehow can regain a bit of knowledge, which looked very good. So we did some more experiments there, tried out more things, but we actually had the problem that in a way it didn't get better and it actually got worse. Because as I said, it's a very challenging environment. And as I said, right, we use this traditional controller to teach the reinforcement learning agent. But we figured out that the reinforcement learning frameworks are quite brittle. So actually, this framework we use there to have this combination of imitation loss with the soft actor critic loss worked in a way somewhat for this setup. and we couldn't figure out why it wasn't getting better. So we tried it to just on a very simple environment, which is this astrolander environment, where you just have this astrolander coming from top, and it should land between these two yellow flags. And it completely screwed up. It was not able to learn anything on this thing. So it seems that the implementation of this combination we had there was not doing well. It somehow was able to learn a bit for whatever reason. We're still trying to figure that out. But it was not able to do anything. So we set it up new and actually just tried what would happen with this new implementation if we just have imitation loss. So in a way, it's always the H-infinity controller taking the decision, and then at some point we turn it off and then see if the system has learned anything. And as you see, it didn't learn anything. So the blue curve is we turned it off quite early, and nothing happens. You see the loss is in the end somehow at random guessing. And here, if you keep it running longer, then you actually see that also the H-infinity controller comes into situations where it cannot control the system anymore, and it dies here around 3 seconds or something, and the thing is completely out of control and it cannot control it anymore. So even our H-infinity controller comes into situations where it doesn't know what the system is doing. One reason for that is, between this implementation and the other implementation, our environment has changed, because we implemented that the H-infinity controller is not allowed to do whatever it likes with the early-on, but actually had some constraints how much it can somehow move it, which in physical world would be a problem. But actually in the first implementation, it was not introduced, which we later found out. So we had to implement it ourselves. And then these situations actually happen that due to the constraints you add to the H-infinity controller, it is actually not able to control this. But as you see, also our reinforcement learning controller currently is not able to control this. We are still working on this. So these plots are actually from the end of last week, where we now actually have the system running again. And we are quite certain that at some point, we actually might at least reconstruct what we had on the plot before, and hopefully actually the system learned a bit, because there's not much talking against it. So it should at least learn what the H-infinity controller knows. At least that is our hope. But it should actually also get better. But fingers crossed, we are not there. I'm sorry that I can't tell you that we have solved everything. We are still working on that research, right? So overall, to sum it up and then come to an end, we have this very complicated environment, which also makes it very interesting, which gives us some sensor readings. And in the end, we want to somehow have a safe controller based on reinforcement learning, which we then can use with help of some shielding mechanism to actually certify the system and then actually implement it first on this Olaf concept and try it out in a wind canal. So don't worry, we do not put it onto an airplane. We first try it out if it really works. But then hopefully at some point we will have this, and then everybody can fly on safely. And on that note, let me finish with a last example. As I said, we are working in this autonomous mobility and logistic facilitation environment. And this is somehow our grand scheme of goals, where we combine all the 4 research departments together into a project, where in the end, the hope is to actually have a factory of the future, as it's called here, where some AI systems, so robots, can interact with humans and interact with each other and are not somehow put on one place and have to stay there, but actually can be reprogrammed to go somewhere else to other jobs and so on. And everything is somehow put into some digital twin and can be monitored and verified, and the world is happy and everything works. And that is the end of my talk. Thank you for your attention.
Right. So now is the time for questions. If you're in the room, just raise your hand. I will give you the mic. If you're online, you can either post your question into the chat and we will know, or you can just unmute yourself and we will hear you too. So are there any questions? Hey.
Yeah, thanks. I have many questions, but I will keep it hopefully short for at first. You said you have like uncertainty quantification, let's say for the example of detecting the human in the working area. Yeah. Does it also make sense to have like a similar metric for certainty quantification that the human left the area?
In a way, yes, definitely. But that would somehow be then the next action, right? In this case, it was just going that the sensor was just uncertain where the human is, and you should somehow quantify that.
Yeah.
But that's somehow the next step, right? You would then include you would have maybe some other sensors, or you would have some time series where it then could look back what happened actually. I'm now uncertain where the human is, and then it might look back with another AI system and say, well, wait a moment, I see that the human actually moved away. And this way you can combine these, and then you say, okay, the human is out of the room, so I can act again as before. But the first step is somehow that the system itself knows something happened. I'm not sure where the human is anymore, and I actually need to do something else. Because you don't want the other system to continuously run, because it might use up too many resources and you might not have them on some small AI device.
And also on similar note, if there are two people, a supervisor comes in, like is there a certainty detector or uncertainty detector of counting how many humans are certainly there and how many humans are hiding behind the bushes?
I'm not sure if they implemented this on the system. The system itself should in the end be used to actually guide visitors to certain rooms they want to go to. So greet them at the elevator, where you then have a certain number of people coming out of the elevator, which you can somehow count, and then bring them to the room and be certain that they actually all come with them, and all of them are there. That's some of the use case we had in mind. So we didn't really implement that other people that come, it should recognize and somehow not bump into them, but it should not somehow pay attention too much to them. They are not somehow important on this task of knowing where the human is, what I showed.
One follow-up questions until my next batch. Like when you have the approach that you showed on the plot of like time dependent kind of aggregate of the uncertainty.
Yeah.
Like, do you address on like, does it make sense to have like multiple uncertainty models, one for like fast, risky behavior or fast movements, and one for slow ones? That like, so you kind of get rid of the jitter of like the sensor when some bright light shines into it, but also like keep it quite fast so it reacts to like fast movements.
Definitely is always good to have as many uncertainty models as possible running side by side. But currently, this was somehow meant to run on this tablet, which only has certain computation resources. So we had to keep it somehow small in the beginning. But definitely, there are improvements we can do, and we are researching on that, how to do that. And yeah, but very good question. Yes.
Right. Any other questions? Right.
I have more general question, because in case of uncertainty, the AI should wait for like human supervision, right?
Depends. It
Depends,
could
yeah.
also activate a second AI system, which is maybe running in the background and helps the first system. But one thing would be that it somehow activates a human expert system in a way.
How does it fit that if the AI will do more and more mundane tasks, how do humans actually keep their expert level knowledge?
Good question. Yeah. let's hope that we don't come to the case where nobody knows how to drive a car anymore, but that is a good case that could happen. But then that's kind of a job, right? To have people actually know this. There's actually a project where another institute is doing research on this. So the DLR has designed and engineered an autonomous car, which somehow really is without a driver, and it's like a shuttle, and you can go in there and sit there. If this system doesn't know what to do anymore, because I don't know, a sensor is broken or there's a situation it just doesn't know what to do, then it actually calls some human operator that somehow sits in some control stand and then sees all the cameras and all the sensors of the system, and can then either tell the system, okay, just continue on what you wanted to do, or actually control the car and drive it out of this dangerous situation. Again, if you have nobody left who could do this task, that's bad. But again, that could be then a job, right? You are trained to drive these autonomous cars out of bad situations. Yeah. Or if you look at it the different way, if you then have interconnected all the cars in the future environment, you could actually have, if you're in a situation where somehow nobody knows what to do, then the other somehow cars in the environment decide, okay, just now go over the street and I wait for you and then you can go on, right? These kind of scenarios will also work. But in the end, somebody has to take a decision. But first of all, you need to know that your actually situation you are in is something you are not known what to do, because that's also a problem with as you probably all know, with, for example, the big foundation models and LLMs like ChatGPT, which always gives you an answer, even though it doesn't know. Right? It will always tell you something, and then it's actually on us to decide it makes it sense or not, which is bad, right? Because at some point we might be in the situation that actually we don't know, and then we have to trust the system, and we should be able to evaluate our trust.
If I understand it correctly, that shielding system in your project is AI as well. And you mentioned that, or is it?
Not that depends. So you can use this actor critic risk network kind of thing, which is not really a shielding, but somehow gives you some safety due to this risk network. But you have to somehow then verify that the risk network knows what an unsafe state is. Or you could use this shielding ansatz we had, where somehow you always need to project down onto some safe actions. But for that, you also, in a way, need to know what is safe. And for that, we had in mind to use this H-infinity controller, which can be programmed on certain actions where it will always control this. But as you might see, there might be situations, and actually, as we actually saw in our study here, there were actually situations where also the controller didn't know what to do. And this has to be put into the system, right? But as soon as you have an AI system as a shield, you also have to shield that system in a way and give formal guarantees.
That's basically my question, because it probably depends if it is possible to have the shielding AI or deterministic on the complexity of the problem you're solving. And then if it is AI, you don't have 100% certainty that it detects what you want to detect. So what is the split between those systems that if you do basically a design in a way that system is so simple that the certainty or uncertainty is that high or low that you basically consider it certain, or what's the split between these systems?
I think this, or maybe if I understand your question correctly, I think it's in the end a combination between symbolic and neurosymbolic methods. So neurosymbolic methods are data-driven, right? You just put data in, it learns, and you can give no deterministic guarantee, at least at the moment, what the system will be doing. It learned on the data, it learned its own features, it decides how it decides. You can try to understand it better by somehow using methods like Shapley values or saliency maps to see what kind, for example, with pictures, what kind of the picture it used for its decision. You can also use methods like combining AI systems with an LLM to actually have the LLM explain what the system does and explain the actions and so on. So combining some of picture segmentation with an LLM, these are methods that are in development that you can do, then you at least have some idea what the system is doing. But in the end, if you want to do a shield where you are very certain what it does, you have to combine it with some symbolic methods where you can really write down if action A happens, next step is action B, and so on. And you can really guarantee that over the whole path that the system might do, there is no unsafe state that happens. And if it might enter an unsafe state, it will take a different decision because the way you set up the system. And in this way, combining symbolic with neurosymbolic methods, you can get a system that is, in a way, completely AI, but you have some safety guarantees, which are not all stochastically, but actually some are deterministic. But that is a current research topic we are heavily working on to actually do this in not only some very basic tasks, but also these kind of heavy tasks where it's actually not clear what is an unsafe state. We have no analytic way to write down when our plane will enter an unsafe state. There is a partial differential equation in the end which governs the system equation, but depending on how fast our airplane is flying, how the initial position of the wings are, and so on, the states change, and actually the decision of the model is then very important because, as you see here, right, the imitation loss, so the H infinity controller knows what kind of action it needs to take, at least if you forget this part, to actually get the systems safe. Also, our AI controller here, the reinforcement learning thing, constantly does some actions. So it's not that it doesn't do anything and decides, okay, I don't know what to do, I will do nothing, but it actually tries to control the system, but it's just not doing enough. That's the problem, right? Or it overdoing it and actually going into another unstable state again. And that's the problem where definitely we need to do more work and understand better what's happening there. And yeah, that's what we are working on. I hope that answers your question.
Any other questions? All right.
Okay, so I would like to ask about the adversarial attacks. If you have tried to, for example, looking at the shield component and how, if you have it as a machine learning model, how sensitive it could be at the end for this kind of topics.
Yep. Good question. We have not looked at this adversarial attacks in this context. But we have especially the department on safety critical, whatever, one of our departments, I've forgotten the name now, sorry for that. They are looking especially in this adversarial attacks and seeing what kind of perturbations can we still control, what kind of perturbations are bad. Can we use, for example, some logical systems to be attached to some neurosymbolic systems to actually help us figure out adversarial attacks? An example would be if you think about traffic sign classification. So a stop sign has corners, a velocity sign is round. And you could, for example, have a second system dissecting the picture and then with some logical methods somehow decide if actually what I'm segmenting has corners or is round. And then if the AI system doing the segmentation decided, oh, this is not a stop sign, but it's actually a 70 kilometers per hour velocity sign. And then the logical system kicks in and says, wait a moment. A velocity sign usually doesn't have, needs to be round, and actually I detect edges. And then you see, okay, I again know there is some uncertainty, probably high uncertainty in this case, hopefully. And then either a third system kicks in or actually the driver is tasked to decide now what to do next, or in a way. And these kind of interplay between different AI systems we are investigating. Yeah. And there also adversarial attacks are quite important in there.
Thank you. So I think, yeah, maybe last question.
just did ask for when you have the shield, like when you have the reinforcement learning, and does the agent take only rewards from the environment, or does it get like punished by the shield system when he wants to do some like unsafe action? Does he get punished? Is it like in the rewards?
No, currently not. So at least in the basic implementation we had with this safety gym environment, we didn't have a punishment in there. It was just trying out if the shielding actually works in a way, and trying to implement so the code is also not ours. We used code from a different paper, but we just wanted to try out, does it really work? Is there an easy way to implement it into our system? And then we figured out, okay, for our plane system, actually, it's not that easy. So for the gym environment, it worked, and we could make it work. But for the air wing fluttering system, we actually have a very complicated reward function, which is quite brittle if you change certain parameters. And so including there some punishment would then it stopped learning anything. So it really was bad. So then we went on to actually start with this imitation learning to actually get to know it into the direction that it actually knows what to do. And we think that at some point we then can somehow activate some shielding process and probably some punishment process later on if it actually has learned to do these basic things there. And then a combination again would hopefully solve the system. But
Thank you.
Nice. So a little bit of organization. First, I wanted to mention that we already know the topic of next Method AI Times. It's going to be people from CTU talking about the autonomous car they built. It is going to happen at the end of January. We will announce it on our meetup page. So, as usual, a week or two in advance, you will learn about it. And yeah, I wanted to mention that for people here, this is not the end. There's more food coming. There's beer on tap, right? We can stick around and talk. And with that, I think we should thank Markus again for the great talk.
thank you.